Myself Dr. W. Begundale from Kamlanand Mahavidyalaya, Nagpur. Today I am going to discuss the chemistry of actinide. In this we are going to see the electronic configuration, position of actinide in the periodic table, and after that oxidation state and atomic and ionic radii. That is, in that case we are going to see what is actinide contraction. So the topic is chemistry of actinide, and today we are going to see some important properties of actinide elements. And as we know that actinides are the 14 elements are there, and these are the block elements and shown separately at the bottom of the periodic table. The group of 14 elements of atomic number 89 onward, that is actinium in the 7th period of the periodic table and corresponding to the filling of 5F subshell are called actinide, and these are similar to the lanthanide in many respects. Among these, only the neptunium and plutonium occur in the nature and in minute quantities, and rest of the elements have been a result of nuclear reactions. These are extremely toxic elements exhibiting biological properties, and this series of 14 elements is also known as actinide, and actinide along with the lanthanides constitute complete F block element. And the ending here, ending IDE in actinide is not appropriate because it more correctly means negative ion such as oxide or chloride. Actinides were also named actinone by group of scientists. However, ending ONE is used preferably for non-metal such as boron, silicon, like that, whereas all the actinides are distinctly metallic. IUPAC has now recommended these elements to be called actinoids with the ending OID rather than being actinides or actinone. And these elements are also named as man-made or synthetic element. These elements are also called as a transuranic element. Transuranic element are elements that have atomic number greater than 92. And these elements are called transuranic because these are the man-made or synthetically synthesized in the laboratory. And after this, now we are going to see the position of actinide in the periodic table. So here, position of this, as we know, this is the periodic table. Here, this is the S block, P block, D block, and the F block. So this first series, 4F series, is the lanthanide, and this is the 5F series, starting from thorium. After actinium, thorium, promethium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, yttrium, fermium, mendelium, nobelium, lawrencium. All these are the 14 elements. Are 5F series is known as the actinide. So they are shown separately at the bottom of the periodic table, and this is the F block element constituted of two series, 5F, 4F series and 5F series. 5F series is the actinide element. So the discovery of these elements follow the discovery of lanthanide, when it was predicted by Seeberg that another inner transition series of elements corresponding to the addition of electron in the 5F shell should also be possible. These elements, which have atomic number greater than 89, are listed in a revised periodic table and outside the main body of the table, just below the lanthanide as shown in the periodic table. So it is important to note that near actinium both the 5F and 6D subshells have almost similar energy. Due to similar energy of 5F and 6D subshell, incoming electron may enter either of the two subshells, which result in the uncertainty of the electronic configuration. As a result, it is doubtful whether electron enter 5F orbital or not. For example, configuration of thorium can be written as 5F0 6D2 7s2 or 5F1 6D1 7s2, like that. Once filling start in F's orbital, the 5F subshell become more stable. Therefore, from uranium onward, the 5F subshell become more stable. Therefore, all the incoming electrons start filling one by one in F orbital. The general electronic configuration of actinides can be written as radon in bracket, and then 5F 0 to 14, 6D 0 to 1, and 7s2. The position of actinide shown in the periodic table is confirmed by the fact that all the elements up to 103 were discovered in the 1961. And so position of these elements are shown in the periodic table. So at the bottom, and two series are there, 4F and 5F. 5F series is the actinide, shown separately at the bottom as a block element and also known as transceramic element. After this, we are going to see the electronic configuration of this actinide, and here this table shows the these are the name of element: actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, yttrium, fermium, mendelium, nobelium, lawrencium, and these are the symbols. And this atom number from actinium are having 89, and from thorium 14 elements are there, start from 90 to 103. And this electronic configuration, that are now atom number 86 and this 389. So start from 5F, 6D1, 7S2. In this way, one by one, the electron goes to the 5F series or 5F orbital here. So the 14 elements that follow actinium, atom number 89, in the periodic table are known as actinide or also known as actinone. They include the three naturally occurring elements, that is thorium, protactinium and uranium, and 11 transceramic elements produced artificially by nuclear reactions. After mercury, we follow 6 elements from therium to radon, in which electron enter the 6p subshell. Radon has the configuration xenon 6s2, 4f14, 5d10, 6p6. At this stage, 7s and 6d subshell have smaller energy relative to the 5f subshell, and next 2 electrons are added to the 7s subshell, and we get francium and radium, which are s block element. We find that 5f and 6d subshell penetrate the 7s orbital quite significantly and are therefore stabilized relative to the 7p subshell. The next few electrons enter either of these two subshells, that is 5f or 6d. And here from the uranium onward, there is no doubt that 5f subshell is more stable. The general electronic configuration of actinides is radon 86, atom number, 5f 0 to 14, 6d 0 to 2 and 7s2. So this is the electronic configuration, and in this case, after uranium, the incoming electron go progressively or field progressively here. In this way, see now here 2, 3, 4, 5, 6, 7, 8, 9, like that up to 14. So this is the electronic configuration of this actinide element. Next property is now oxidation state of actinide, and as we know, oxidation state may be positive, negative, may be minimum, maximum. In this case, oxidation state is minimum 2 in case of some element, and maximum is 7, and common oxidation state again shown by the +3 oxidation state is the common, and in this case, in this table, the oxidation state shown in the bracket are unstable, and stable oxidation state are shown by the bold. These are the bold oxidation state which are stable, and here are common oxidation state, and so +3 is the common oxidation state. In this case, maximum is +7 oxidation state, minimum is +2. So these elements of actinide also show variable oxidation state. The actinide elements show greater range of oxidation state as compared to lanthanide element. The various oxidation state of these elements are shown in this table, in this slide, and it is also noted that oxidation state shown in the bracket are unstable. Bold numbers are most common oxidation state of the actinide element. +2 oxidation state in case of actinides is very rare and shown by some element. Americium 2+ has the electronic configuration 5f7. It is similar to europium EU2+ in the lanthanide, but exists only in the solid state. So some elements show +2, and +3 oxidation state is the most common oxidation state among all the actinide elements. However, this is not always the more stable oxidation state of actinide. The first 4 elements, thorium, paramecium, uranium, neptunium, do not show +3 oxidation state as the most stable oxidation state. For example, uranium 3+ is readily oxidized in air as well as in solution. The most stable oxidation state of element up to uranium is the one involving all the valence electron. The most stable oxidation state of thorium, paramecium and uranium are +4, +5 and +6, like that. However, neptunium shows the oxidation state +7 by involving all its valence electron. It is not the most stable state. Neptunium in +7 oxidation state is highly oxidizing, and the most stable state is +5. Now in some element also show +4 oxidation state, and from thorium to californium. However, paramecium and neptunium show +4 oxidation state. In case of some element, +5 oxidation state is shown by all the element from paramecium to americium. However, +5 oxidation state is more stable for paramecium and neptunium. +6 oxidation state is shown by lower actinides, that is uranium, neptunium, plutonium, americium, in the form of their fluoride. The +6 oxidation state is more commonly found as the dioxo ion, and +6 oxidation state is a compound or uranyl nitrate dihydrate, like that. +7 oxidation state is known only in the oxocation of neptunium and plutonium. When alkaline solutions are oxidized by oxygen, the important oxonium known in case of neptunium plutoniums are formed. So these are the different variable oxidation state. So minimum is +2, maximum is +7, common oxidation state shown is a +3. And in this case of table, those oxidation states shown by bold are stable. Next property that we are going to see is the atomic and ionic radii of the element. And here the size of actinide ion, decreases regularly along the actinide series. This is because with increasing atomic number, the extra charge on the nucleus is poorly screened by the F electron. This decrease in ionic radii with the increase in atomic number is known as the actinide contraction, similar to the lanthanide contraction. The comparison of metal 3+ ionic radii of actinide with those of lanthanide shown in this slide, in this figure, and in this shows very similar in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of M3+ and M4+ ion in case of actinide shown here in this figure. And so here this is the actinide 3+, actinide 4+, and this is the metallic actinide. So there is no more change because of the similarity properties. There is no any variation, and similarity is shown in case of 3+3 and +4. It is seen clearly from the now also table is shown here, radii of actinide cation, and from this table it is clear that tripositive and tetrapositive actinide ions are in the actinide contraction analogous to the lanthanide contraction as we go from one element to other in the actinide series. The atomic number and nuclear charge increases by 1 unit. It is also known that shielding of one electron present in the F orbital by another electron also present in the same orbital is very poor. Because of this, the valence shield in each successive actinide is brought closer to the nucleus with increase in nuclear charge by +1 unit. Hence, the size of metal 3+ and 4+ ion decreases progressively from one element to other, resulting in actinide contraction. So some values are shown here for decrease in the atomic and radii of these actinide cations. So this is the see the values decreases. This is the radii value, and in case of M4+, these are the elements, and radii it show the decrease. So in case of this 3+ ion, in case of 4+ ion, radii value both are, but not much variation, very close to each other because of the similarity in the properties. So these are the properties of actinide series. So today we have seen the chemistry of actinide, in which we have seen 4 important properties. One is the position of actinide in the periodic table, and they are shown at the bottom of the periodic table after the lanthanide series. And then we have seen the electronic configuration of the element, and after that atomic and ionic radii and oxidation state shown by the actinide elements.